I will begin with a word of prayer. Excuse me. Dearly Father, we thank you for this day again. I thank you for this class, for these students. Just ask you just bless our work today, help us to glorify you and what we do, and just to ask good questions as we think of them, Lord. In your name I pray, Lord Jesus. Amen. So I have a bit of a cold, and so I wrote that up on the board so that I have it there. Do you guys have any questions about homework, though, before I use those things? Yeah.
There's the first question in problem 17, which says, it's an equation for a hyperbola, but it says to find the parametrization in the plane.
Yeah, so like x and y. There's no z. Yeah. So like I think I wrote the formulas down for that in the first week at some point, but use caution cinch as appropriate, right? So other questions? Yep.
Permits for 28 have the lines intersect.
Oh, just a second. Let me get on the same page as you. Problem 28. If I can find it. Well, you don't want to look at the solution. Let's see here. Oh, you're asking me about the hard one. All right, fine. Suppose two ninja begin traveling in paths given below. So I give you two different paths. One starts at t equal to 0. The other one also starts at t equal to 0. And then, let's see here. So what's your question about it?
Is that asking just whether the lines intersect?
Well, I think that's for you to decide, right? What would be a reasonable interpretation of the problem?
If they intersect, then the June and we will follow the same that trail.
But, well, I mean, maybe. But what if they intersect in such a way that the time of the intersection is, what if the Jonan crosses the path of the other one before he's there? So it's not quite intersection. It's intersection where the tracking ninja has to cross the path of the other one at a time after he was crossing that point, if that makes sense. So it's kind of a modified intersection problem, but yeah. But we worked an intersection problem in class, right? You just write down the one parameterization for t, the other parameterization for s, and just try to see if you can find an s and a t which solve. And in general, if you just try to do this for arbitrary curves, you can't solve it. The algebra is just too formidable. But these are lines, so it shouldn't be too bad. Other questions? Well, you can still ask questions tomorrow, so it's all good. Let's look at one example in the notes while I've got this thing out. Oh man, come on, stop that. So like this example here is particularly simple because, well, first of all, it's a circle, right? And second of all, I've already parameterized the circle with respect to arc length, right? So, listen, here, if you look at my notes, this V I also denote as S dot. S dot is a notation for ds dt. It is the magnitude of the velocity vector. All right? It's all these things. So you have, these are all equal, all right? Now, a unit speed curve has the v, the speed, equal to 1. So the formulas for the, like the curvature and the torsion of a unit speed curve are like easier. You don't have to divide by the speed. I mean, it's not a lot easier, but it's a little bit easier. And so let's see here. So there's the given parameterization of the circle. And then I differentiate. That gives me the unit tangent, right? And look at it. It's already a unit vector. I don't have to normalize it because, by the way, what's normalizing? Normalizing a vector is making it into a unit vector, right? So like in our system of measurement, let's suppose we're using meters. If you were to be normalized, it would require some amount of surgery for you guys. You know, you don't want to be normalized. Like you have your height reset at 1 meter, that would be painful, you know? Just saying. All right, idiotic comments aside, going on. So that's the unit tangent. And then if we differentiate the unit tangent, what do we get? Well, the derivative of the unit tangent right here, dt ds, is that. And if you look at that, the magnitude of dt ds tilde is exactly 1 over r. But notice that the magnitude, oh man, look at that. My bad. That's supposed to be length of the vector. So the curvature is just the magnitude of the derivative of the unit tangent for a unit speed curve, because the v is equal to 1, so that formula simplifies. It's just the magnitude of the derivative of d tilde ds. And for that, here, the length of this vector, because you've got a cosine inside, like this right here is a unit vector, right? So the thing out front is its length, its magnitude, and so we get curvature as 1 over r. And then finally, when you take the cross product of the t tilde and the n tilde, you get the binormal, which in this case is constant. It's 0, 0, 1. Which is to say that this circle lies in the xy plane, and the normal to the xy plane is what? It's just z hat, right? It's just 0, 0, 1. And no matter where you are in the circle, t cross n always gives you z hat as you go around the circle. I don't have enough flexibility in my arm to go all the way around, but I could draw a picture in a second here. All right? So that's just a warm-up example. Let's actually calculate one from front to back, the whole deal. All right? And then maybe we'll come back to the notes if I start hacking and coughing and stuff. All right. In the interest of that not happening, I stole some bubble gum from my 6-year-old. So don't tell him. Oh. 5-second rule? No. Not today.
I have vitamin dense meal if you want some.
Thank you, but just as funnier. For the sake of the comedy. And also, if you chew gum in math videos and post them on YouTube, it ticks off a certain set of people. It's very unprofessional. How dare you chew gum in lecture? Oh, they're out there. I always tell them that they get what they pay for. My channel's not monetized, you know. I probably should monetize it. You know?
Not over 10,000 subscribers.
If I monetized it and I made some merch, you know, maybe I could be, you know, independently wealthy in no time. All right. So the picture of what I was just talking about, that I mentioned, is just this. So like, the circle is in the xy plane, and if you can picture, the unit tangent is like this. The unit normal points to it points to the center of the circle if you study it, right? It points to the center of the circle if you study. Those are supposed to be equal length vectors. You get the idea. But what happens when you take t cross n there? So t crossed into n, if we're talking about a circle in the plane, right? If the circle's in the plane, as we take t and we cross it into n, as we go around the circle, we're always the same. It's always the same binormal. Because the circle, I will eventually find a red marker, is a planar curve. All right? So that's a picture of the one that I just projected, right? That's why the binormal was constant, 0, 0, 1, all the way around, because Even though the direction of the tangent and the normal is changing as you're going around, they're always, cross product is held constant. The next example I'm going to do will not be this way. And I'm going to work an example with some letters because that gets us more bang for our buck. All right, so this is a pretty standard example. I think if you study my previous Calculus 3 tests from sort of an actuarial perspective, what you'll find is that there's about an 80% chance this problem or something really like it is on the first test in this course. Sometimes with numbers, sometimes with letters. But here's the problem. You're given a path, all right? Calculate the Frenet frame. That is, calculate the TNB vector fields to this curve, all right? And what else? And calculate the curvature and torsion for this curve. Now, this curve is what? Let me tell you what it is before we do any kind of calculations. What you're looking at here is a helix. All right? Start something like here, and then it just kind of goes up, right? Now, I start time at 0 just for the sake of my picture not being too hard to draw. But of course, if you allow time to go negative, it keeps going down, right? So it's basically like a slinky, if you guys ever played with slinky. All right, so let's get to it. Let us calculate the tangent, the normal, the binormal. Start with the velocity. What's the velocity to this curve? By the way, that's a gamma. What we got? Is there?
Negative r sine.
Okay. That's not a question for me. Let's go on here. Minus r sine t, r cosine t, derivative of m, t? Well, just m. All right, so here I'm thinking of r and m as being constants, all right? You guys with me? What's the speed here? You guys calculate it for me. What's the speed of this curve? How do you calculate the speed?
Square root of r squared plus m squared.
Right? So the speed is equal to the square root of r squared sine squared t plus r squared cosine squared t plus m squared, which you already were so kind as to simplify for me as to the square root of r squared plus m squared, right? Because sine squared plus cosine squared is 1. So while this curve is not as simple as a circle, it's also a very nice curve because it does have constant speed, right? It is a constant speed curve, which makes it a particularly nice example for this course because the calculations are not too onerous. All right, so well then what's the unit tangent? What's the unit tangent? T is 1 over v times v, right? It's the normalized velocity vector field, which in this case is 1 over the square root of r squared plus m squared, all right, times minus r sine t, r cosine t, m. And for a problem like this, I am perfectly happy. And in fact, I would prefer it if you had a constant factor like that, if you left it factored out. It's better for you to leave that out than to multiply it through and write it 3 times. All right? There's a time and place for multiplying numbers through vectors. This is not it. Like, leave it out. Okay? Then what? Well, then we have to calculate the, oh no, great, googly moogly. Does this look right to you? What else have I done today? Man. So this was supposed to be t prime, right? T prime. That prime matters, otherwise it's not a unit vector and doesn't really tell us anything new. All right, so t prime. So let us calculate dt dt. Now, see, the beautiful thing is we can pull that constant and leave it out front. Just leave it out there. It's minding its own business. Just leave it out front. It's a constant. We differentiate right past it. What's the derivative of minus r sine t? Minus r cosine t, right? That one is minus r sine t and 0. Let me hazard a picture here. What's going on? Well, the tangent vector maybe looks, I'll try it here, looks something like this, right? But what's the normal vector look like? Notice it has no z component. Oh, we're not to the normal vector yet. What's the normal vector? It is a unit vector in the direction of this. What's the magnitude of dt dt? So this is a positive constant, so you can just pull that out, all right? You can just pull that out, right? Do you guys know which property I'm using? Let me make sure you understand what I'm doing there. We have a property for the length of a vector. If you have the length of a vector, a scalar multiple, let's say c times a vector v, let's say vector w, then that's the absolute value of c times the length of w, right? But the thing is, if c is a positive, or at least a non-negative constant, then the absolute value of c is just c again. So that's the case with this constant here. It's just a positive constant. So we can pull it out of the length, and we're just up against the length of this vector, right? Which is what? R squared cosine squared t, right? Plus r squared sine squared t, which some of you have already seen is r. Sorry, that was just me. You guys aren't idiots. All right, so we're pirates. Let's see here, r squared plus m squared. So apparently the magnitude of dt dt is that. All right, and what does that make the normal vector? The normal vector, which of course is 1 over the length of dt dt times dt dt. Well, that's exactly minus cosine t minus sine t 0. So there is the normal vector. Listen, as you're calculating the t and the n and the b, if you're doing your calculation right, you should have unit vectors, right? Listen, I'll be honest with you. Do I actually think about dividing this number into that vector? I'll be honest with you, I don't. What I do is I look at this and I think I can pull an r out, and then I've got r over the square root of r squared plus m squared times the vector minus cosine minus sine 0. And I know that's a unit vector, so I know I'm right. I know that's the n. So if you can see a unit vector in the formula of a vector you're trying to normalize, just take it. You don't actually have to do the division. Yeah.
How do you know it's unit?
Because cosine squared plus sine squared is 1. Yeah. So my point is, okay, there's n, right? What direction does n go? I violated my color coding, my bad. But n, notice, I don't know, up to the limits of my artistry, n is, you know, it's like, I don't know if I can capture this or not, but that should be like parallel, right? To xy plane. It's just pointing towards the axis around which the helix is twisting, right? It's pointing directly towards the axis. That's the way the normal points. On the other hand, the tangent vector, it's pointing up and it's twisting around, right? It's kind of a combination of the theta hat I talked about before as well as z hat. Some linear combination of those two things. All right, so we got our t, we got our n. Wait a minute, can we calculate the curvature? We can. We have everything we need because we know the magnitude of dt dt. We know the speed. So let's calculate the curvature. What's the curvature? By the way, curvature, and we could have done this before I wrote down the n, right? The curvature is 1 over the speed times the magnitude of dt dt, which is what here? It's 1 over the square root of r squared plus m squared times r divided by the square root of r squared plus m squared. So cleaning it up over here, excuse me, the curvature at time t, it's not really I mean, here it's kind of a boring function of t because it's constant. It's r divided by r squared plus m squared. Right? That's the curvature for the helix. Let's kind of stop to appreciate that formula for a second. So the bigger, if the radius, right? Think about this. If the radius of the helix is much, much bigger than m, right? If the radius of the helix is like huge compared to m, what does this look like? Right, it's like 1 over r if m is much, much greater than r. And it's approximately equal to what? It's approximately equal to... Yeah. It definitely should. So sad. And then the other limit, what would happen? What happens if m is much, much bigger than r? I mean, it's approximately 0, right, if m is much, much greater than r, because that just kills it. I would say technically, so think about those two extremes geometrically. What are we talking about? If the m is really, really small compared to r, you're basically just talking about a slightly elevated circle, right? It's basically just a circle. So the radius is the curvature is 1 over the radius, like I projected before this example, right? For a circle, the curvature is 1 over the radius. On the other hand, the curvature is 0 if m is like huge compared to r. What would happen if m is huge compared to r? That basically just means it's the z-axis, right? It's just a line in that limiting sense. Now, technically speaking, that's outside our scope, right? Because the Frenet frame only works for a non-stop, nonlinear curve. So like, technically speaking, it's outside our context here, but one would expect reasonably that the curvature of a line should be 0. Lines are not curved. They have 0 curvature. That's something we would like. That's an intuitive idea. Okay, so then what is left? So let's go down the list. We've calculated the tangent. We calculated the normal. We calculated the curvature. Now we need to calculate the binormal. What's the binormal? T cross n, right? So we got to take, 1 over the square root of r squared plus m squared, and we got ourselves a minus r sine t, r cosine t, m. We're supposed to take the the cross product rather, with the normal, which is just simply minus cosine minus sine 0. But this is a cross product, so by now you guys are bored of these, right? You can do these, I hope. Let's see here, what do we get? What do we get? I'll leave the constant out front. All right. So let's see here. I get minus m sine t from the 2, wait a minute, 3, oh, that's a plus, isn't it? Let me think about this a second, guys. Z hat cross y hat would be a minus, yeah, so m sine t. We'll check my work here in just a second. Z, so minus m. I know there's like 1 sign in here from memory. And then that's 0. And then the z component is more interesting because it's 1, 2, which gives me a r sine squared t plus r cosine squared t, which of course simplifies to 1 over the square root of r squared plus m squared m sine t minus m cos t r, or r if you prefer. So there you go. That's the binormal. Pretty much the same vector length calculation we did for the speed at the start of this calculation shows you that the length of the vector that I've written there is exactly, the length of it is exactly the square root of r squared plus m squared, right? So it checks that the binormal is a unit vector, see, because this vector has length square root of m squared plus r squared. So when you divide by that, you've got a unit vector. Hooray. So there's our binormal. Now how do we calculate the torsion? Torsion's kind of a doozy, isn't it? We're supposed to take minus 1 over, we need to calculate dB dt dot n. So let's do that. What's dB dt, first of all? The derivative of the torsion. So that's easy enough to calculate. Square root of r squared plus m squared. M cos t, m sine t, and then, well, 0, right? So what's dB dt dot n equal to? I'll write it out here. My n was just minus cosine t minus sine t, right? 0. It's been a minute since I wrote it. Yeah. So there's dB dt dot n. And how does that work out? If you like sine squared plus cosine squared equals to 1, this is a problem for you, right? We got lots of that. Yeah, we get minus m cosine squared t minus m sine squared t divided by square root of r squared plus m squared, right? Also known as minus m over the square root of r squared plus m squared. Now what's the formula for torsion, though? Torsion is given by, there's a minus sign in there, right? Minus 1 over the speed times dB dt dot n. And so the torsion is equal to minus 1 over the square root of r squared plus m squared times minus m over the square root of r squared plus m squared. So clean it up, what you got? What's the torsion equal to? The torsion is m over r squared plus m squared. Now, let's appreciate some different cases, right? What happens if m equals to 0? What happens if m equals 0? M equals 0. The torsion is equal to 0. By the way, it's a circle. It's literally a circle. If m equals to 0, this formula drops back to the circle of radius r in the xy plane centered at the origin, right? So yeah, it's got radius 1 over r, and it's got torsion 0. It's a planar curve. So that's about all I got to say. I mean, otherwise, the larger m is, let's see here. I guess we could say this. This is approximately what? 1 over m for m greater, much greater than r, right? If the radius is negligible compared to the slope of the helix, then the torsion is essentially 1 over m. The torsion is something like the reciprocal of the slope of the helix, ignoring the radius, I guess, if I didn't calculate that wrong. I don't think so. So the bigger m is, wait, this seems wrong. Is that right? The bigger m is, sorry, I'm confused all of a sudden. Or something I'm saying this wrong, because the bigger m is for, well, if we fix r and we make m larger, the torsion should be This is not a question I should think about today. Sorry, guys. I'm trying to think about what would make the torsion bigger. Like, what does torsion describe? It's describing how the curve is lifting up off the plane in which it's going, right? It's like it's how the curve is twisting up, if it is. This one is. So, I don't know. I'm not sure how useful this comment is. I'm gonna rescind it for the moment. A day I'm less sick, I'll try to say something about it, perhaps. Any questions? So, if I give you a curve, can you calculate the TNB frame? You can. It's just a matter of one step after the other, right? We start with differentiating, we find the velocity curve, we normalize it, that gives us the unit tangent, right? Along the way there, we found the speed. Then, once you have that, you differentiate that, that gives you dt dt. You normalize that, that gives you the normal. As you're doing that, if you look at the magnitude of dt dt, we've already found the curvature, if we remember the formula for curvature here, right? 1 over the speed times the magnitude of dt dt. And then once you've got the normal and you've got the tangent, you take the cross product of those things, you get the binormal. And then if you want to calculate the torsion, you have to calculate the derivative of the binormal, take the dot product with the normal. That divided by the speed with a minus sign is the torsion. So every step here is pretty straightforward. There's just a lot of steps, right? So this is a wonderful test question because what does it test? Like everything, right? It's got dot products, it's got cross products, it's got, you know, all the kinds of derivatives that you need to know in here, right? Lengths of vectors galore. It's just a good problem. There's a lot here. Yeah.
In the previous test, you mentioned how curvature is also equal to dt tilde over ds. Is that the same thing as 1 over d?
So, kappa tilde of s is equal to the magnitude of dt tilde ds because v is equal to 1 for the unit speed. And I mean, if you read my notes, like my point is we should define the curvature and the torsion in terms of the unit speed curve, so it has a concrete, unambiguous geometric definition, because you know up to where you start the arc length, there's a unique, unit speed curve, and it's pretty obvious that if you started the arc length a different place, it wouldn't change the derivative of the, these derivatives would be unaltered by a change of where you start the arc length. So defining the curvature and the torsion in terms of the unit speed curve gives us a geometric, for sure, not dependent on the parameterization idea of curvature, torsion, and also the TNB frame. See, because whenever you calculate these things with respect to parameterization, it begs another question, which is, how do you know that if I calculated the curvature or the torsion with respect to a different parameterization of the curve, that I wouldn't get a different curvature and torsion? Well, I know that doesn't happen because I defined the curvature and the torsion in terms of the unit speed, and then I simply use the chain rule to derive those formulas. So that's a way of us avoiding a discussion about how to change the parameter on curves and then sort through how the calculus changes as under a change of parameter. There comes a time and a place that discussion can't be avoided. For us, it's the integral. Like eventually we'll have to talk about how integrals, we're going to define integrals in this course with respect to like parameterizations of curves. So it begs a question, how do you know that the integral that you set up isn't dependent on your choice of parameterization for the curve? So I do have some proofs later in the notes, like that the line integral that we define later, and then the surface integral that we define after that are independent of our choice of parameterization for the curve we're integrating over, or the surface we're parametrizing. But we're not there yet, right? You guys are still just kind of dipping your toes in the pond and getting used to what in the world of parameterization even is, right? It's still weird and new, I think. Because in calculus 2, what do? We hide what it really is by just talking about parametric equations, which kind of just makes it into a formulaic kind of thing. It really robs you of the deeper ideas. Now, one of you asked me like what my method was for parameterizing a curve, and like it's wonderful that if you ask this question, because that means that you're one step closer to understanding that there is no method. So parameterizing a curve it's an art form. It's not something that has a ironclad, you do this, then this, then this. It's not like that. It's more educated guessing. And what constitutes a parameterization or doesn't constitute a parameterization depends on how you're describing the curve. You know, if you've got a pair of surfaces and your curve is like a curve of intersection, well then you have to solve both equations that define the curve, right? That's simple enough. But there are other ways of defining curves. Like you could say it's like it's a circle on a plane or something, and then you might have to use like a geometric construction to build the formula, essentially to build your own XY coordinate system on a plane to set up the formulas for a hyperbola or an ellipse or something. You know, we could do things like that. But let me go on. One other thing I should talk about. Oh man, this motion. Let me try to take a stab at that in 3D. Right? So in this case, I talk r is equal to r of t is position, right? V of t is what? Velocity, right? It's instantaneous velocity. That's the only kind of velocity we care about in calculus. It's also a vector, right? It's a vector. And then acceleration is, and I'm an idiot. It's also equal to dr dt, right? Duh. And the acceleration is, well, it's dv dt, or if you like, it's d squared r dt squared. I think I wrote these things down before another day, but it doesn't hurt to write them down again. I want to, now that we know a little bit more about how to describe the geometry of a curve, let's try to use the tangent, normal, and binormal vectors to describe the velocity and the acceleration. What can we say? What's the interplay between the TNB idea and physics? I'll start out with the easy part, right? The most easy part is that the velocity, well, it's the speed times t, right? Where, so like the velocity is just your speed times your unit tangent. That's pretty easy, right? Agree? I mean, I hope you agree. Then what? Yowzers. I'll write on the middle board so you guys can see better. I don't think we need this anymore. All right, so now that I'll write it again here. We have the velocity is the speed times the unit tangent, right? Wonderful. What's acceleration equal to? It's dv dt, right? By definition. But what else is that? Well, that's d dt of the speed times the unit tangent. This is a scalar function times a vector function. We know that there's a product rule, right? And so, do the product rule. We got what? We've got dv dt times t plus v times dt dt. Now, do you guys remember? May not remember. I don't think I even wrote them down on the board yet. But you guys remember the Frenet-Serre equation? What was dt dt equal to? We said it was equal to the curvature times n. Now I'm forgetting off the top of my head. Let me think. Yeah, we have to multiply by v. Yeah, so we don't know its unit speed, so we have to multiply by the speed here. So this is one of the Frenet-Serre equations. But that means that I can rewrite dt dt in terms of the normal vector, right? So this is by the way, this is S double dot times T plus V times kappa Vn. Let me complete my datification of this formula here. So S double dot times T I've been here a while. And I cannot remember the last time I saw some dude come up to some other dude and go, nice pants. Like, it just doesn't happen. You do it all the time?
Yeah, I saw a dude beautiful in the gym the other day.
See, this is why I don't go to the gym. Let's see here. So, S dot squared kappa. Also, I think it costs money. But anyway, listen, S is what? Remember, S is S dot. S dot is ds dt. That's the speed, right? The magnitude of the velocity. But S double dot is the it's the change in the speed per unit time. It's not the acceleration, right? It's the rate of change of the speed. And there you have it. I mean, this right here tells you how the acceleration vector goes in terms of the Fresnel-Serre frame. And it shows you that the acceleration vector, it has to point in either the tangent or the normal direction. The acceleration vector cannot have a binormal component. Check this out. You can calculate the tangential component, a sub t, right? A sub t is equal to a dot t by definition, okay? So this is the projection onto the t direction of a. It's the scalar component of a in the t direction, the so-called tangential acceleration. The formula for the tangential acceleration is just straight up s double dot. The formula for the normal acceleration, on the other hand, is what? It's a dot n, and what's that work out to here? Well, take the dot product of the equation above, right? N dot t is 0. So when we take the dot product, we just select the component, the coefficient of the vector we're looking at the component of. In other words, a dot n just gives me s dot squared kappa, right? Let me put that in more familiar terms. The curvature is 1 over the radius. It's 1 over the radius along which the curve is traveling, all right? S dot is v. So what you're looking at there is exactly v squared over r. So what this says is that if the curvature is non-zero, there's a portion of the acceleration vector which is proportional to the square of the velocity divided by the radius, and it points towards the center of the circle of motion. This is exactly the centripetal acceleration formula we show you guys in physics, right? That's the centripetal acceleration. It's center seeking because our Fresnel normal is center seeking. Any questions? No? Let me show you some pictures of this. It's gonna be a fun day. Thing is, with this 8:15 class, I'm never gonna get better. Like, I'm gonna be sick the rest of this semester. Pretty much, like, I tell you. All right, well, I've got this thing out. Let me just mention, and we can work out we can work out some more examples another day, right? But like, here's another example. This one, let's talk about what this is. See that? It's kind of like the helix, except what? I mean, there's something sort of helical about it. It speeds up as it goes is one thing. It's kind of tricksy. And like what I would think of as the radius, right? If you think about x squared plus y squared, you get e to the t as your radius. So it's something like a spiral. It's more like a spiral that's exponentially growing bigger and bigger as it goes out. Something like a spiral helix. But anyway, the calculation is the same way we just went through. I differentiate it. This one, calculating the length of the vector is a little bit, more troublesome, but it works out to 2 there. That does. And so the unit tangent ends up being this. And then normalizing, well, differentiating again, I get that, which then I can calculate the magnitude of this vector, and from that I can find the curvature as this. So, but the calculation's the same we just did. It's just uglier, right? Just uglier. All right, let me not get distracted. I want to show you some pictures while I have this thing out. All right, so like this one's the one I want to show you. So here's an example. The acceleration, right? The acceleration is the blue vector because what I'm picturing here is just, this. Ignoring the twisting and, motion about the center of mass of the marker. We'll leave that for physics, right? But that's projectile motion to a good approximation. Ignoring air friction, stuff like that, and the fact that it's actually elliptical because it's a bound orbit around the center of mass. Anyway, blah, blah. So approximately parabolic. And so it looks like this, and it's because the acceleration is 9.8 meters per second squared downward, right? But that acceleration vector always can be divided into a tangential and a normal component. And so I'm graphing the tangential component, right? But you can see that well, I made it that far. I made it that far. You can see, if you use your imagination, that to get this vector from that vector, I'd have to also add the center seeking around. If you can, I mean, goodness gracious. Yeah, this is just the velocity vector, I think. Those are not unit tangents, obviously. That's part of the problem. Well, not just a problem, but it's... Anyway, my point is, you can decompose the acceleration vector into a normal. And like here, this one, this is the picture if you're talking about a curve that's going with constant speed around a circle. So then the acceleration has no tangential component, it's just center seeking. But if you're speeding up as you're going around, then you pick up a tangential component to the acceleration. So the picture is different. And like, well, anyway, I think that's good for today. Let me put you out of your misery. So. Again, we have time for questions, so ask them if you got them tomorrow.